in chapter 7 is to learn what are called electron configurations. So before you even get into the notes part, I just want to go into that term. What do you think electron configurations mean? What does configuration mean? Where they're placed. Yeah. What's another word for that? You're giving me like some other synonyms of configuration. What'd you say? Yeah, how it's built. Yep. Where things are placed, how it's built, the arrangement of things, right? How things are put together. Those are all examples of configuration. So when we talk about electron configurations, we're looking at how electrons are arranged in an atom. Okay? Typically, everything we've done so far is just talking about how many electrons are present, right? But we haven't really given much thought to where are they located, how are they arranged, where do they sit, all those types of things. And so that's really what we're going to dive into in this chapter. Now, I want you to give you like a long-range picture of where we're going. We're starting with kind of the base electron configuration, and we're going to figure out where are they located, where do they sit. But our goal is to get through the chapter and be able to give every electron basically an address. Like we're going to know exactly where it's located, exactly what part of the atom it's located in, exactly what direction it's spinning. We're going to give it a lot of detail to it, okay? So our goal for the end of our chapter is to be able to give every electron an address, okay? So that's our big picture here. But we're going to start with giving it like, if we were talking in terms of its address, today we're going to figure out like what city it lives in. That's kind of where we're going, right? We're going to narrow it down where they're at, but we're not going to get too specific yet, okay? So we're going to do something called electron configurations. When we talk about electron configurations for us right now, we're going to deal with something called ground state electron configurations. And that just means we're going to look at electrons when they're in their like lowest and most relaxed state. So we're not worried about things that are out of place or not following rules. We're going to start with what we consider ground state. So if everything's like going as planned, right? Everything's following what it's supposed to be. All right, so we're going to be able to give a ground state electron configuration for every element. You'll be able to list every element's electron arrangements. Okay? So to get there, we need to give some background and some of our we need to give some information. So I want to tell you that what we're talking about in terms of where electrons are located is about the atom specifically, but the patterns are mimicked perfectly on the periodic table. Okay, the area in which electrons are located, these patterns are perfectly mimicked on the periodic table. So let's kind of dive through what is happening here. Okay, you see this periodic table is broken into 4 regions or 4 blocks, they call them. S block, P block, D block, and F block. Okay, those correspond to 4 types of orbitals. Okay, and let me tell you what an orbital is basically an electron pocket. Where electrons are located is called an orbital. And there are 4 categories of orbitals, S, P, D, and F, type orbitals. And so if an element is located in an S block, what that means is that its outermost electron is found in an S-shaped orbital. Okay, let me say that again. If an element is located in the P block, that means the last electron to go into that element is located in a P orbital. Okay, so 4 different types of orbitals, S, P, D, and F. And they have different shapes and they have different sizes and different properties, but those are the 4 categories of orbitals. And so if we have an element that's in the P block, like carbon, that would mean that carbon's last electron, at least, is located in a P-shaped orbital. Does that kind of make sense? So what I want you to write on your periodic table is I want you to have it marked off that like these are S elements. These 6 right here are P block. You could write them as P block, or you could just write an S and a P. And these ones right here, the transition elements in the middle, these are all D. And then the lanthanides and the actinides down here are F. Okay, so I want you to give a label to those. So the S group, the S orbitals or S block is just these 2 groups right here. D block is all the transition metals. P is over here, all of these elements. And F is right over here. Okay, so let's give our periodic table at least just like a basic label of those regions. And again, we're going to do it enough that you're going to become so familiar with it. So don't feel like you need to overmark it on your periodic table. You're going to become super familiar with what we're doing. So Just give it a little bit of a region or however you want to lay it out, but that'll give you an idea of where they're located at. Okay, the next slide I'm going to show you has even more detail in its labeling system. I don't think you need to necessarily label this on your periodic table, but I want to give you an idea of what it looks like. Okay, so do we have these ones written out? Yeah. S, P, D, and F? Okay, so let me give you a little more detail here about how it's laid out. Okay, this didn't print very well, so I'm going to clear this real quick. Let's rewrite these. Okay. As we're looking at writing or figuring out where our electrons are located, we need to label them a little bit more. So this is called a period, right? A period goes across. Are we good with that? We remember that part? Oh, goodness. Okay, period goes across. So we have 1, 2, 3, 4, 5, not 7, 5, 6, 7. We have 7 periods found on the periodic table. That also mimics the number of energy levels or the number of levels of electrons that an atom can have. It can have up to 7 levels of electrons. Okay, so the way we know how many levels an electron has is that every time that an element basically goes from a noble gas and we flip down to the next line on our periodic table, right? When we go from neon, sorry, that didn't print very well. When we go from neon down here to sodium, we add another level of shells of electrons, okay? So every time we move down a row on the periodic table, think of it as like us adding a layer of electrons to our element. That's why our element gets bigger and bigger and bigger the farther we go down, because we have more levels of electrons. So if we're down here, 1, 2, 3, 4, 5, that means any element in this row has basically 5 levels of electrons. Okay, we kind of add another shell to it. Okay, I think probably the word shell is a better word to use there, but we've got that many shells worth of electrons. Yeah? Mm-hmm. Okay, so we label those in there as 1, 2, 3, 4, 5, 6, 7. So we can have electrons, let's say for francium. Francium's last electron is found in the 7s orbital. Okay, do you see what we're saying? Level 7, and it's in the s block, right, for francium. So what would barium's last electron be in what? 6s. Good. What about potassium? It would be 4s. Perfect. Do you see what I'm saying? Its last electron. When we talk about the electron configuration for potassium, we're really talking about where is its last electron. That's really what we're focusing on. Electron number 19. Agreed? Okay. So the s orbitals, they go perfectly. The p orbitals go perfectly. But I want you to notice one thing. There's no set of orbitals that are called 1p orbitals, are there? The first row of the periodic table, or the first period, only has 2 elements, hydrogen and helium. And then we go down and get a new shell. So there is no such thing as a 1p orbital.
Wait, so helium isn't?
Helium actually is part of the s block. Oh. So even though it sits on the other side of the periodic table, the 1s orbital, it only holds 2 electrons, and so it's already full by that time. Okay? Now, the p orbitals start at 2 and they go down just like normally. But here's where we get a little bit different. Do you notice how this is the 4th level, but we see an orbital called 3d? Yeah, it's tricky, okay? This is something that we have to kind of memorize, is that if we have an element in this block, its electrons are actually found in the 3d orbital, even though it doesn't fit like that on the periodic table. We just have to memorize that. This is 3, 4, 5, 6d. So that means there's no such thing as 7d orbitals or 1 or 2. Okay, we'll talk about these as we go through, but they get filled in this exact order. We fill our 4s, then we fill 3d and 4p. Okay, how are we feeling? I was looking at zinc, which is right here. Its last electron is in what type of orbital? 3d, right, 3d. Okay, and then like bromine, where's bromine at? Bromine's last electron is in, I don't think 5. 1, 2, 3, 4p. Right, you have to count helium's row, which is like 1, but we don't have a 1p orbital. 2, 3, 4p. Okay? All right, let's keep going here just a little bit. Let's look at the s orbitals specifically, okay? The s orbital, I skipped that slide. Okay, I don't have that one on here. Sorry. Let's look at the s orbital. Okay, and review here a little bit the definition of an orbital. I'm sure there's a fancy book definition, but I just basically call orbitals electron pockets. They're places where electron exists. Okay, they have kind of loose boundaries. It's not like a balloon, right, where we have a really hard boundary. This is just the electron region where they're located. Okay, I'm sure the book has a fancier definition, but I don't know what it is. Okay, I consider orbitals to be electron pockets. And we said there's 4 types, S, P, D, and F. So S orbitals are the very first ones that we have. S orbitals. They are shaped like a sphere. So just that shape. Okay, it's a sphere shape. I want you to go ahead and write this down. I don't know why this didn't get included, but I just must have left it off by accident. Okay, they are a sphere shape. Now, every type of orbital holds kind of a different number of electrons. That's a little bit of a tricky statement. But S orbitals in particular can only hold 2 electrons. That's so important, okay? Highlight that, circle it, do whatever you want to do, but the S orbitals specifically can only hold 2 electrons. And if I forget that, I can look up at the S block and say, oh, there's 2 groups found in the S block. So 2 right there tells me it can hold 2 electrons. You see what I'm saying? 2 groups located in the S block, it can hold 2 electrons. Okay? All right. Let's move into the next category of orbital over here. How many groups are in the P block? 1, 2, 3, 4, 5, 6. Right? So that pattern is perfectly mimicked on the periodic table. The S block element, the S orbital, it can hold 2. P can hold 6 total. Okay? Now, are a sphere shaped, which is P orbitals. Okay, there are 3 different versions of P orbitals. 1, 2, 3. I don't really need you to know the versions of the P orbitals. I don't really care about that. This is what they look like in kind of 3 dimensions. They're like little, I kind of draw them like this shape. Kind of like little propeller or a little dumbbell. I don't know what you want to say, but this little shape. And there's 3 versions that can fit around the nucleus. Okay, so like here's version 1, here's version 2, here's version 3, right? And they all sit around the nucleus, just a little bit different, but they fit together in this puzzle. You see what I'm saying? Okay, so there are 3 versions of the P orbitals. Now, each version can hold 2 electrons. So there's 2 electrons here, 2 electrons here, 2 electrons here. So how many electrons in total can the P group hold? 6. So this P orbitals can hold 6 electrons in total. 6 electrons in total. Now, look back at our move to the D orbitals. See how the shapes get much more intense here of our D orbitals? We have a lot more flexibility, like a lot of different things happening here. They don't even show an overlay. But here are 5 versions of the d orbitals, and those are all supposed to fit together over the nucleus simultaneously. Right? That's crazy looking, okay? But again, remember, it's not really a hard boundary. Do you see this? This is what it's really looking like here. Those are all like electron clouds that they've been able to visualize and see where these electrons are located. Okay, so that's like every dot that's represented there is like where they found the electron at one point in time. Okay, so it's just like this little cloud they've drawn. But if these are the d orbitals and there are 5 versions that can each hold 2 electrons, how many total can the d orbitals hold? 10 electrons total. And guess what? If we count the d block, we're going to see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? All of those patterns are mimicked on the periodic table. Okay, are you hanging with me? Okay, we're going to get to it. I promise. My slide for last one is F orbitals. This is where things just get crazy. Okay, we don't dive too much into the F orbitals because periodic tables draw them a little bit differently. See how on our periodic table La and AC are down in the lanthanides and actinides? But then what about your printed one? Where are they on your printed one?
They're down there.
They're down there too? Okay, on my printed one, La and AC are up here in the regular periodic table, and they bumped them. So they're a little bit different. So we don't talk a lot about them.
Are they right there?
Yeah, mine are in that little blank spot right there. Yep. But the F orbitals theoretically fit right up here, right? Number 56 to 57. So where they fit at is a little bit different. We're not too concerned with the f orbitals, but that's where things get really crazy. Look how stretched out they have to be, right? You see those electron pockets are really stretched out because it's so taken up with an s, then p, and then d, right? And so now our f orbitals get really full. How many do you think they can hold in total? 14 electrons. 7 different versions. 1, 2, 3, 4, 5, 6, 7 versions. They can each hold that. Or again, count them along here. 1, 2, 3, you'll find 14. So all of these numbers, these patterns, show up on the periodic table for us, which is helpful. Okay? So let's try some. Okay? We're going to try to start giving some electron configurations. And I don't think I printed a slide necessarily for us to do practice on. So you can just do them off to the side or in your...
Electron configurations.
Right, I don't have that on me, okay? Let's start with kind of a simple one. Let's try beryllium. Let's try beryllium. Be. Okay, beryllium. I want the electron configuration for beryllium. And I haven't even really showed you how they get written out. But I'm going to give you beryllium and let's see what we can do from there. Okay, so beryllium's electron configuration looks like this. 1s2, 2s2. So I want you to try to tell me what do these symbols and numbers mean? What are they telling us? Okay, it is telling me the level. I have 1s listed and I have 2s listed. And what do you think these numbers up here mean?
The number
Squared?
No, not squared. Good thought.
electrons.
The number of electrons.
It's like they can hold.
That's right. That's the number of electrons that are found in that particular orbital. So when we look at beryllium, we know we have to have 4 electrons in our configuration because that's how many electrons beryllium has. And so to get to beryllium, we have to fill up the 1s orbital. And then now we've got to move down and start right here with the 2s orbital. And beryllium is the second one in there.
So if you do like zinc, you're going to have to write all of them.
Yes, you are. Mayo, good observation. I love it. Okay, Anthony, what's your question?
Nothing.
Okay. So let's look, boron is the next element. So its electron configuration would look the same. 1s2, 2s2, and then we'd move on to the 2p orbitals. And boron, where is it? Is it the first one in there? Is it the second one, third one, fourth, fifth? So 1 electron in the 2p orbitals. I'm just looking at where is the element located in that p block, and that tells me how many electrons are found in that orbital. And then if I want to check my answer, I take my electron numbers and I add them up, and for boron, I should have 5 electrons, which is what I do.
Wait, but like, why is it?
Next one. Let's try titanium. Let's try titanium. So we're going to get a little bit of a wrinkle here, but not too bad. Titanium. So in order to get to titanium, I think the best thing for us to do is just work our way across the periodic table. Okay, so the first orbital that comes is 1s. Does it have to be full?
Yes.
Yes, everything has to be full until we get to titanium. So I'm going to write out 1s. It can hold 2 electrons. The next one is 2s, and it has to be full, right? Then I move across, and now I'm at 2p. Is it going to be full?
Yes.
Yes, and the p can hold 6, right? 1, 2, 3, 4, 5, 6. Now I'm at neon, right? But I'm not done yet. I got to keep going. So I'm going to go to the next one, and sodium is 3s, and is it full? Yes, here's our answer. Everything has to be full until we get to titanium. All of our orbitals have to be full until we get to 22. So I'm done with sodium and magnesium. I'm going to move over to where aluminum is, which is 3p, and it can hold 6. So now what element basically am I at? Where have I filled? How many electrons have I put in?
18.
I put in 18, right? I put in 18 electrons, and so I'm at a full 3p6 orbital. Now I'm going to go down here to where potassium is. I'm basically assigning a location for electron number 19 and 20 right here. Okay, so this is 4s2. And now I'm going to go to titanium, which is in 3d, and how many?
2.
3d2. That's it.
Wait, what?
That's it. How do I know it's 3d2?
Because you count like how many.
It's just the second element right there. And if I want to check my answer, I'm going to add them up. 2, 4, 10, 12, 18, 20, 22 electrons, which is what titanium is supposed to have. How do we feel about that? Okay?
Yeah.
Some yes, some no. I will tell you this like this every single class, every single year. It's like so crazy confusing until you get it, and then it's just like, oh yeah, that's so easy. Okay, so just stay with me if it's not there yet. What if I was going to do chlorine? Okay, let's try chlorine. Chlorine. What does chlorine end with? Sometimes that's even an easier way to get started. What does chlorine end with? 3P, right? I know this is P block. That's automatic P block. 1, 2, 3P. 3P what? 3P5, right? 1, 2, 3, 4, 5. So 3P5 will be what we end with. We have to fill everything up to that point. Okay, so 1s2, 2s2, 2p6, 3s2, 3p5. Okay. Say that? Okay. But we'll go. Abbreviating electron configuration, or some people call this noble gas configuration. Okay. Why do you think it might be called? Okay, let me think about this. Why do you think we would abbreviate electron configuration with noble gases? Why would that be like important? Why would we choose noble gases to abbreviate our electron configurations? What's specific about the noble gas group? Right, neon, argon, krypton, all those things. How many valence electrons do they have? Do you remember that? No. Okay. Do you know what valence electrons are? Electrons in the outermost shell. Okay. The noble gases have full S and P shells. They have 8 total electrons in their outer shells, right? S and P. They're filled up. So a noble gas, if we get all the way to noble gases, neon, argon, krypton, you know what I mean when I say noble gases? If we get all the way over there, that means they have full electrons. So we're only going to abbreviate our electron configurations with something that is full. Okay? So the way we do this is we abbreviate it with a noble gas, and then we list everything that comes after that. Okay? So let's say that we wanted to find the electron configuration of calcium, and we're going to abbreviate it. Okay? So let's find where calcium is. Right here. What's the noble gas that comes before calcium? Argon. Okay? So argon's electron configuration and calcium's configuration are the same up to that point. So we put argon in parentheses, right? If we're trying to find calcium, we put argon in parentheses and we say it's the same as argon plus 4s2.
What are all the noble gases?
The noble gases are all the light green. So helium, neon, argon, krypton, all of those guys are the noble gases. So group 8, okay? And they have full shells, right? And what we know about electron configurations is that when we fill that P shell, that means we're full, right? And then we start a new shell of electrons when we come down here. So that's full. So abbreviated electron configurations are just showing us that calcium's configuration is the same as argon, plus whatever comes after that, 4s2. Let's try a couple other ones here. Let's try iron. Okay. Do we see iron number 26? We work backwards and find what is the noble gas that comes before iron. Yeah, it's argon also. So for iron, we're going to say it's the same as argon. And then we just have to list everything that comes after argon until we get to iron. Okay, so it would be argon, then what?
3s2.
Not 3s, but 4s2. I think it's 4.
Yeah, it is.
4. Okay, 4s2, then 3d6. Now, a common mistake is for people to say, oh, it's argon, then go right to 3d6. But we have to list anything that comes after that. Okay, does that make sense? Okay, you also cannot abbreviate something with itself. So if I wanted an abbreviated configuration for argon, I can't just put argon in parentheses. Okay, I have to go to the one before that and then fill it. Okay? All right, try, where is TE? Try this one. TE. Tellurilium is over there, number 52. Try that one on your own and let's see how it goes. Is that what we had?
No, I'm at 46. I forgot it was 10.
4D. Okay, yeah. Yep. 4D. The d orbitals get 10. And if we can't remember that, then just count across and figure out how many there are because that'll match. So there's 10 like groups of that block. So we'll count them across. Okay, how are we feeling? Yes, kind of. Okay, remember that our goal for this, what we're doing with this whole thing, is we're saying that for tellurium, its last electron is 5 levels away from the nucleus in the p-shaped orbital. That's what we're doing, right? We said we're kind of getting ourselves to a city-state situation, right? We don't have the full address yet, but we have at least a region. Where is it located? Right, we know that it's in the 5th energy level from 5th shell from the nucleus, and we know that it's in an orbital that has a P shape, right? And then as we go the next couple of days, we're going to be able to really pinpoint its location and list its address. But for right now, we at least know how far away it is, all that kind of stuff. Okay? What would you do if I said, give me the electron configuration? Let's try this one together, okay? Not abbreviated, but what would you do if I said, give me the electron configuration for O minus 2, the ion oxide? What would you do differently there? If I'm asking you for, give me the electron configuration for the last electron in oxide with a minus 2 charge.
Just change all the exponents to negative.
Oh, okay, good thought, but no, we won't have to do that. What does the negative 2 tell me about oxygen here?
2 less electrons.
Not 2 less, but
2 more.
2 extra. I would just have 2 extra electrons on oxygen, wouldn't I? If I have an oxygen with a negative 2 charge, that means I've got 2 extra electrons present. And so if that's true, what will the electron configuration really look like?
It'd be like...
Won't it just look like neon's electron configuration?
Yeah.
Yeah, it would be like I'm representing whatever atom it has, but with 10 electrons instead of 8. Do you see what I'm saying?
Yeah.
So we don't know when we write an electron configuration, if you just see an electron configuration, it might be for a neutral atom, but it might also be for an ion, right? When we solve it backwards like that, we'll always go with it's a neutral atom. But in all reality, the electron configuration for oxygen with a minus 2 charge and fluorine with a minus 1 charge and neon, they all look the same, right? Because they all have 10 electrons. Okay, yeah, go ahead.
If it would have like a minus 3, you just add another electron, or do you
Yeah.
go back down to...
You add another electron. If it would be oxygen minus 3, that'd be a weird scenario, but if you did, it would just look like sodium. Just the same if I said a sodium with a plus 1 charge. We would go backwards to neon. Yeah. Okay, the last thing I'm going to do, I'm going to have you identify the element based on its electron configuration. I actually think this is a lot easier because you just have to pinpoint it on the periodic table, right? So let's say that it is xenon. Okay, let's see that is our element we're trying to identify. We assume it's a neutral atom. Are you ready to shout it out?
Yeah.
What is it? 1, 2, 3, go.
Cesium.
Yeah, good. Cesium. I should have picked one that's easier to say. Cesium, right? I know it's krypton plus 6s1. Do I really even care what comes at the beginning here?
No.
I really don't. All I need to do is locate where's 6s1, right? Well, I know it's right there. That's got to be it. Okay? The same thing would be true if I gave you this big long electron configuration and it ended with 4p5, right? If it ends in 4p5, what element is it? What is it? 4p5.
Rome.
Yeah. Probably 1, 2, 3, 4, 5. Yeah. So we don't really care about what comes at the beginning, right? The last thing tells us kind of what element we're at. Very good? Okay. I'm going to stop us there with notes for today. We've got about 30 minutes, and I've got a CK12 posted for you that I would like for you to work on. But if you have questions as you're working through it, I'm happy to help you answer those questions.